what we left from the first lecture, and then we'll talk about string theory. So we were talking about black holes. And so I said that a black hole is a Schwarzschild solution that is valid until the apparent singularity at 2 mgn. And when we reach 2 mgn, we have an infinite time for a light ray to reach it, or reversely, from something from the event horizon to reach us. And I've also said that in general relativity, if we have all the invariants finite, means it's not really a singularity. And that means that we should be able to find some set of coordinates which makes that apparent. And those set of coordinates were found by Kruskal. So in order to describe them, first one changes to so-called tortoise coordinates. So first, tortoise coordinates u t minus r star, v t plus r star. Tortoise coordinates where r star is equal to r plus 2 mgn log r over 2 mgn minus 1. And then Eddington-Finkelstein coordinates, which are light-like. And finally, the Kruskal coordinates, which are these ones. U bar is minus 4 mgn, e to the u over 4 mgn, and v bar is plus 4 mgn, e to the v over 4 mgn. So these seem like interesting, simple enough coordinate transformations. And the metric, if we do this, is minus 2 mgn over r, e minus r over 2 mgn, du bar, dv bar, plus, of course, r squared d omega squared. And the interesting thing is that now there doesn't appear to be any singularity anymore at r equal to 0. So r is defined, of course, implicitly via these transformations. But r equal to 0 used to be singular. Now it's not singular anymore. And moreover, the region r greater than 2 mgn is mapped to u bar negative and v bar positive. So this is just one set of possibilities, and it's immediately obvious that we could extend. You just look at this metric, and you see there's nothing special happening at u bar equal to 0 and v bar equal to 0, so we can extend over the whole R2, the domain of validity. And yeah, so there's nothing special which can be seen also by calculating u bar v bar. calculating U bar, V bar, and we get this relation, e to the r over 2 mgn. Yeah, minus over 4 mgn squared, and r over 2 mgn minus 1. So it's clear that U bar equal to 0 or V bar equal to 0 corresponds to R equal to the horizon, R equal to mgn. However, in the metric, nothing particularly different happens there. So we can describe in these coordinates U bar and V bar. We can describe this region U bar less than 0 and V bar greater than 0 as region 1. So remember, U bar and V bar are light-like coordinates. So it's a light-like quadrant. But then we can extend, as we said, we can extend to over the whole real line, both U bar and V bar, which amounts to, in this diagram, to extending over the other 4 quadrants. Just that, looking at this relation, we see that R equal to 0, which is the true singularity, corresponds to U bar, V bar. There's some constant which is positive, right? So there's a minus sign here and minus sign here. So this is some constant which is positive, which are these 2 parabolae. So this is known as a Kruskal diagram, but we can draw the Penrose diagram. And for that, we need to make some more coordinate transformations from U bar to and V bar to U bar plus and U bar minus. So again with a tangent. And 4 mgn in front. And finally, as before, since these are U bar plus, U bar minus are still light-like, we write tau plus minus theta over 2. And in order to figure out where to put the singularity in here, we put R equal to 0, and then this amounts to the formula written over there, which I'll not repeat, but that amounts to sine squared tau over 2. So tau is the time-like coordinate. Sine squared tau over 2 is equal to 1/2, which means tau is plus minus pi over 2. All right, so what is the Penrose diagram then? Well, once again, we have the same thing. So like for flat space, also for AdS, also now we start with a diamond, because the metric is still as you can see in here, I have a conformal factor, well, not with a minus, I have a conformal factor, but then I have still flat space, minus d bar dv bar. So I have the same, and U bar and V bar were extended to the full real line. So I would draw the same diamond, excuse me, diamond Penrose diagram. Right? Except now I have an endpoint for the true singularity r equal to 0, which is tau equal plus minus over 2. So one is here, and one is here. So this was tau and theta. And remember, we're keeping light at 45 degrees always, so I keep this structure of the Kruskal diagram. So I have this. And now let me take this out to be a little bit more obvious. Okay, and this is 1, 2, 3, and 4. So that's the Penrose diagram of the black hole. But there is, now we look at it, there is an interpretation issue here because, excuse me, because, there's one more observation which I was making, that the horizon, which is u bar or v bar equal to 0, corresponded to this light-like line. So these are the horizons. And so there's a horizon in the future, but also a horizon in the past. And also there's this other asymptotic region that completely mirrors the asymptotic region we're in. So this is not what an astrophysical object would have. This is what is known as the eternal black hole. One that has always existed, so both in the past and the future, and has these other regions. So if I consider a black hole that is created through a collapse, then certainly I will have only half of this, right? So I have this half, really. So, and I will not have a singularity in the past, because in the past I have nothing. I have just dust collapsing. So this would be the horizon, and here would be my collapsing dust or star or so. Okay, so this is the true diagram of a collapsing black hole. All right, so that was the things we couldn't say, we didn't have time to say in the first lecture. And now I will change gears and I will talk about string theory and D-branes, the second lecture. Okay, so in order to understand string theory, we must think of particles first, and then generalizing. That's always a good idea when doing physics. You start with the simplest model you can have, and then you generalize. So, particles first. Well, it's not just particles, but we have to think of particles from the point of view of the line which they span as they move, the so-called world line. So how would I write an action for this? Well, it has to be an action on the world line, so integral d tau, where this is the proper time. Then it has to have the mass. Mass times gives a dimensional thing, so that's fine. And then we introduce this thing. So this is what? This is just dx mu, dx nu, eta mu, d tau, which is ds squared over d tau squared. So with a minus, that would be just 1, right? ds squared for a time-like direction is just minus d tau squared. Sorry. Except, of course, when I write this, I mean that these are now functions of time. So my variable now is the trajectory of the particle, x mu of tau. And to check that this action is correct, I can write the non-relativistic approximation and then introduce also, remember the fact that I have dropped the speed of light, c equal 1. So I put it back in, integral d tau. And here x0 is tau, so I get 1 for the first. And these others give me the velocity divided by c squared, so velocity, but I put back in c. And see, then if I expand, sorry, this is equal. If I expand the square root, I get integral d tau minus mc squared plus mv squared over 2. So potential plus kinetic energy, right? So that's the correct action for a particle. So this is the generalization in special relativity. And we can see that the action has this reparametrization invariance, or general coordinate transformation in one dimension, proper time. And we can find the equations of motion of this. So remember, the variables are x mu of tau. So we vary with the action with respect to x mu of tau. We do a partial integration, and we get the result there on page 27. It's a total derivative. But the total derivative is of what? The thing that appears in there. So the square root itself of minus x dot is 1. And here I have eta mu x dot mu, which is times an m on the outside, so I get minus p mu. So right, so for arbitrary variations, the equation of motion is that this is equal to 0, which is indeed the equation of motion of a free particle. The momentum is constant. But there's also a boundary term, comes from some partial integration. M dx mu d tau at boundaries, at tau initial and tau final. This also should be put to 0 and should give boundary conditions. At this moment, it's not particularly deep. It just says that the momentum is the same at the initial and final points. But I want you to keep this in mind, excuse me, for the generalization to strings. And coupling to gravity just means replacing this with an arbitrary metric, so g mu nu of x And another generalization is which makes us understand better this generalization with, by adding a metric, is if I add a background charge, this means what? So the coupling of a gauge field with a current is A mu J mu. But the position x is now considered only along the world line, so x of tau. And J mu itself is considered now as the current of a moving charge. Right? So this becomes just, sorry. So now this becomes just integral d tau a mu of x of tau. Yeah, I should have left it like this. And then doing the integration of the delta function, I get a mu of x of tau times q dx mu d tau. And so this would be a term that I would add if I have a coupling to a background charge. So I would to a background field of and a charge on the world line. So I would add a term that depends on this background field, A mu, and is defined over the world line. Now this is similar to this, right? I have some background field, G mu nu in here, and the action is defined over the line. And now, one more generalization. You know, again, this is kind of not very deep for a particle, but the whole point is to understand the particle in all possible details so that we can generalize. So now, we write, this is a nonlinear action with two derivatives. So this is a second order action, just like we had for general relativity. So now we would want to write a first order action. So how do we write that? Well, first of all, what are the variables? Well, so this one, it's in one dimension, but you can think of it as having, so if I want to describe it in terms of general relativity, you can think of it as having a metric on the one-dimensional world line. And I would write this as the square, now it's a true square, it's not, there are no issues with matrices, of an Einbein field. Ein is one, field is many, so in this case it's just one. And square root minus determinant gamma then would become, sorry, with a minus, then would become just this, E of tau. And if I multiply with gamma tau tau up, this would be E minus 1 of tau. So if I write an action for general relativity on the one-dimensional line, I would write what? Well, this x of tau is a scalar. If I have a reparameterization tau prime of tau, the position does not change, right? So x prime of tau prime is equal to x of tau from a point of view of the reparameterization. So this is a scalar. And if I write an action for a scalar, it's 1/2, right? The derivative for the scalar, derivative for the scalar, right? Except the scalars are contracted with eta mu. And here I have only tau, I have nothing else. And then I would have normally square root of the metric times the inverse metric. But this is just e minus 1 of tau now. And I could also write a term that is invariant, that is just square root determinant gamma, that is E of tau, times the mass. So this is, I've written here just thinking about the scalars and possible terms. But the point is to write a first order action for that. And then, of course, you have to figure out that these coefficients in here have the proper values. And it's indeed true. You vary with respect to E of tau. And you get that, well, E squared of tau is x dot mu over m squared. Right? And then substituting back in. So yeah, I vary with respect to E of tau, then I get indeed this. Here I have x dot squared, and here vary I get E minus 2, here vary I get nothing. So this is the result. And then I substitute back in, and I get back the original action. So this is indeed a first order action. Meaning it has reduced, so okay, derivatives, this is still quadratic in derivatives, but it has reduced the nonlinearity of this action into a simple action with just quadratic fields, free action. And there's an new independent variable, E of tau, which when varied gives back the original one. Okay? All right. Then the interesting thing is, so this first order action is better than the second order one. Why? Well, in here, if I would take m to 0, like I need for a light-like particle, this would be singular. But here I just drop this term. And moreover, I said that I have a reparameterization invariance, which now I can fix this reparameterization invariance by one function, tau prime of tau. I can fix one function, E of tau, such that E of tau is equal to 1. So at least the degrees of freedom match, but you can check that you can actually do it. So with one function, fix this other function. So then the action which I get is integral d tau, 1/2 integral d tau, x dot mu eta mu. Okay? And what happens when I do this? Well, there's an equation. This still has the variable x mu of tau. So I have still the equation of motion that I wrote there, d tau p mu equal to 0. I still have this equation of motion. But now this comes from a gauge fix, a constraint, right? Think Maxwell theory in the Coulomb gauge, let's say, right? If I do that, then I get a constraint. In that case, got the Gauss constraint. So the constraint corresponds to the equation of motion of the thing that was fixed, right? So the thing that was fixed was, in this case, E of tau, right? E of tau was fixed, was supposed to be 1, so this is the corresponding constraint, right? Just that if I look in here, and I remember that for a general metric, I get G mu nu in here, and moreover, in terms of 1 dimensions, in principle, there would be a gamma of time in here. So the equation that x squared is equal to 1 yeah, not to. I was talking about m equal to 0 limit. So the m equal to 0 limit means really x squared equal to 0, right? Because here I divided by m squared to get this. So now I cannot divide anymore. This goes away. When I vary with respect to E, I get just x squared equal to 0. And this is then the energy momentum tensor for this scalar action, for this action for matter. So I vary with respect to the metric, I get an energy momentum tensor, and then this is equal to 0. Okay, so we understood the particle. And now it's just generalizing to the strings. Okay? All right, so the first action, the Nambu-Goto action, is just the equivalent of our original second-order action for the particle. So the second-order action for the particle was just the integral of the proper time along the path. So now for some, I told you I cannot draw. Anyway, this is supposed to be what the string spans as it goes through space. This would be called the world sheet. Just like for particle, it was a world line. And so I have a direction sigma along the string, and a direction tau, excuse me, which is like the proper time. And so the action would be just the integral of this world sheet, just like over there the action was the integral of the world line. And so the coefficient in front, well, there it was called the mass, but now for a string, it's by definition called minus 1 over 2 pi alpha prime, then d2 sigma square root dA x mu dB x nu g mu nu eta AB. Okay, this would be what I would what I would write, well, sorry, to be more precise, so I would write this as minus determinant, so minus determinant of HAB, where, so this is now the same logic as for general relativity, so this is the invariant integration measure in 2 dimensions, right? But if it's second order, I have to define this metric HAB as a metric induced by the embedding of the world sheet. So HAB would be dA x mu dB x nu g mu nu of x. Okay. And just like we had reparametrization invariance for the particle, now we have, well, more general ones. Diffeomorphism or general coordinate, it has several names, right? Diffeomorphism, general coordinate transformation, or reparametrization invariance also if you want. So just invariance under, sorry, sigma A is, sigma prime A is sigma prime A of sigma B on the 2-dimensional world sheet. And again, if I want to introduce a first order action, I have to introduce an auxiliary field. And the auxiliary field, in the case of the particle, was this Einbein, 1-dimensional equivalent of the field bind. But I could have chosen it to be, through this relation, I could have chosen it to be the 1-dimensional metric, gamma tau tau. And in the case of the 2-dimensional world sheet, it is better to think of it, of the auxiliary field, as the independent world sheet metric, although I could still consider the field bind. So that gives us the Polyakov action, right? So I have, it's the same thing, it's just that now I have this 2 pi alpha prime in front. And again, what I'm considering the equivalent of is this action for the massless particle, because I want to think, so here the massless particle was a photon or something. Now I want to think of a relativistic string with endpoints moving at the speed of light. I don't want to think of a non-relativistic string, something like a vortex line or something like that. No, this is a fundamental relativistic string, okay? So I have d2 sigma square root, I called it gamma, no? Okay, minus, let's say, determinant gamma, okay? And then the same gamma AB, dA, x mu, dB, x nu, g mu nu, right? So it's really this kind of action, right? Here, this stood for E-1 stood for square root determinant gamma times gamma inverse, and here is the same thing. And now, what are the symmetries of this thing? This has more symmetries. So it's a more complicated action, has more symmetries. It has, well, I mean, it has Poincaré invariance in space-time, right? If I consider just the metric, the flat metrics, then I would have Poincaré invariance. Poincaré means Lorentz plus translations. Then I have the diffeomorphisms, or general coordinate transformations on the world sheet. Then I have one more transformation that is new, this Weil invariance. So the multiplication by some function by some conformal factor of the metric on the world sheet. And so this is an invariance of space-time, and it's only valid for eta mu nu. If I have g mu nu, it's not there. But these are always there. The diffeomorphisms, or general coordinate, and Weil are always there. And how many are there? Well, general coordinate transformations is two functions, right? For A being corresponding to tau and sigma. And Weil is one function. Is this, how do I call it? Omega of sigma and tau. Right? So three functions. But that's, in fact, the same number of independent components of a metric, which is a symmetric 2x2 matrix. So I have three functions. This is the same as this, right? So just by counting degrees of freedom, it's clear, you can be more precise, but it's clear that you can put this metric to the flat metric, to eta AB. So this is a gauge, just like we had a gauge for diffeomorphisms in here. Yeah. Yeah. So indeed, there's what the question was what happens when you go to the quantum level? Is it more profound, the fact that we have more symmetries? Indeed. So at the quantum level, first order and second order actions in general would not necessarily give the same results. Only at the classical level give the same, because the equations of motion are the same. But at the quantum level, it's not clear. Excuse me. So we will always consider the action with more symmetries to be more fundamental, because it's easier to work with. But yeah, it's not entirely obvious that, excuse me, that the two give the same results at the quantum level. Yeah. Auxiliary fields? I am not sure of what would be a better way to, I mean, this looks as simple as you can get, right? So, yeah, I don't know what else. So, yeah, because when I put this, these things just becomes eta AB, right? So, yeah, I mean, what's simpler than this? Not much. Okay, so then the action becomes, as we said, and this is the action of massless scalars in 2 dimensions, right? And this now still has some invariance. So you say, well, we fixed the invariance. Yeah, but remember, the same thing happens with Maxwell. If you fix, if you count the number of degrees of freedom and you fix this same number, you can still have a residual gauge invariance that depends in a specific way on the space-time parameters, right? So what happens in Maxwell case, for instance, you fix, excuse me, you fix, let's say, the Coulomb gauge, because it's a little bit clearer relating to this. You fix the Coulomb gauge, you can still fix the Lorentz gauge on top of that, getting you the radiation gauge, right? Even though you count the number of degrees of freedom, fixing Coulomb gauge seems like you get rid of, it's 1 degree of freedom, like the 1 degree of freedom you need to get rid of. But still, you're left with more a residual symmetry. And the same thing happens here. We're left with a residual symmetry called conformal invariance. And the equations of motion then of this action, well, this is just a quadratic action. It's clear that the equations of motion are just the free wave equation. So the equations of motion are just free waves. So just box mu sigma tau equal to 0, right? And you can write this as this. You can write box as this. And that means it's clear that the most general solution is a part that depends on sigma plus tau and the part that depends on sigma minus tau. Okay? Left moving and right moving. I can never remember which is left, which is right. It's a definition anyway, but I think I got the same. Yeah. Okay, we'll see to that when we get to the. So the question was what happens to the string tension. We'll see to a little bit later on. So this is the equation of motion, but well, I erased it. But there was in the analogy with the particle, you have the equation of motion for the particles, which was just dp mu d tau equals 0. And then, it's a little bit, you can see. And then there was a boundary term that also needed to be put to 0. So now we get the equation of motion, this. And then there's a boundary term that needs to be put to 0. Right? It's just that this boundary term now, it's a little bit more complicated. So I still have delta x mu. And then I have d sigma x mu at sigma equal to 0, sigma equal to L equal to 0. Okay? And this, the fact that this term needs to vanish leads to several possibilities. So I can have closed strings which means periodic boundary conditions. Right? What's at sigma equal to 0 is the same as sigma equal to L. So that's a possibility. The other is Neumann open strings. Which amounts to putting this equal to 0 at the boundaries. So this sigma x mu equal to 0 at sigma equal to 0 and L. And also, Dirichlet open strings, which amounts to putting this to 0. That's also a possibility. So delta x mu equal to 0 at 0 and L, which means x mu equal to some constant. Okay, so those are the possibilities. And yeah, so then let's see. So I also calculate the I can also calculate the energy momentum tensor, which, as I said, is defined by -2 over square root gamma ds d gamma AB. But for simplicity, in string theory, it's also defined by an extra factor. So instead of these two, I have 1 over 4 pi. Okay, and we get, I will not repeat, so you have the formula on page 32. So you have T01, T11, 00, 11. These are the 3 independent ones. So this is x dot x prime, and this is x dot squared plus x prime squared over 2. And and remember what I told you, when I fix some gauge, I need to put the equation of motion of the thing that I fixed to 0. Otherwise, it doesn't make sense. And I fixed the gauge for gamma AB. That means, like for the particle, I have to put to 0 its equation of motion, or in other words, this TAB. So this is 0, this is 0. All right. Now, expanding this general form in terms of a left moving and the right moving mode, we get that long formula, page 32, but that's just first some center of mass motion, and then expansion in Fourier for the closed string. For the closed string. So closed string means a circle, so I can do a Fourier expansion. That's basically what I wrote there. Some coefficients for the expansion of this into Fourier coefficients, and then another coefficient for the expansion of this. All right. And then I need to put, on top of that, as I said, I need to put to 0 these constraints. But one useful way is to consider the Fourier modes of these constraints as well. And do some calculations, find these things. It's not important for me at this point. The only thing I want you to note is that the 0 modes, L0 and L0 bar of these constraints, when summed, give a Hamiltonian. So this is in the case of the closed string, and you can do the same thing for an open string and find, in that case, it's just L0. And this equation, L0 plus L0 bar equal to 0, since x mu contains also the p mu's, not just the alpha n's, but also the p mu's. The condition, once you calculate it, turns out to be minus p squared, which I define to be as the mass squared, or center of motion, right? Center of motion mass squared. I mean, minus p mu squared is always m squared of the string. This has some expression in terms of the alphas. So alpha alpha plus alpha tilde. So minus n and minus n. Okay. Yeah, I don't know how this thing is over there. Okay. But so the next thing is to now quantize the string. So we have written an expansion in terms of alpha and mu's and alpha tilde and mu's, and the p's are related to these. Okay, so these coefficients appear just as classical coefficients in the expansion of the solution. But now if I go to a quantum theory, so in the quantum theory, this is basically just a generalization of the harmonic oscillator. For the harmonic oscillator, you have a coefficient, which is a coefficient of the harmonic motion, that, when getting quantized, becomes an operator, an A and an A dagger, right? The same thing happens here, it's just we have an infinite number of A's and an infinite number of A daggers. So at the quantum level, we get that this alpha mu minus m up to a numerical factor is an A dagger. And with plus is just A. Okay. And there's still the conformal invariance to think about. So there's still some gauge invariance some invariance that needs to be fixed. So when fixing that in a particular way, in the so-called light cone gauge, so let's say light cone gauge, then we find, so this is one more constraint on our solution, and we find then that x minus is a function of the rest, right? And then x plus is part of the gauge condition, so it's also, so it's gauge condition. And so the only independent variables are xi, which are transverse. So that's nothing new for us. It's kind of the same thing that happens for Maxwell theory. We have, once we've fixed all the gauges, we have only transverse modes, which are physical, and the time-like and longitudinal one, which are not. Time-like or longitudinal, which can be said to be plus or minus. It's the same thing. So we have only, the spectrum is defined only in terms of these longitudinal modes. So only alpha minus n I are the relevant ones. And you look at this mass squared relation. So now it's written only in terms of alpha and i's. And first, one observation is that one finds, so when going from a classical to a quantum theory, I have to define the order of operators, right? I always have to, like, X and P, I have to say, or in this case, A and A dagger. So defining the order, in this case, amounts, so in here in particular, in this sum, I have A's and A daggers. When doing that correctly, you find the relation written there on page 33. So that m squared is 1 over alpha prime, a number operator, minus A, and A is a constant that becomes d minus 2 over 24. But then you have to do a little bit of physical input. And one way to, I mean, so this is an integer. One way to see that, so certainly this has to be an integer, but actually it needs to be 1, such that you have an object, so in the case of closed strings, let's say, or no, here I wrote for the open string. So in the case of open strings, I can have the thing with a single A dagger. This thing has a transverse index I. So this thing looks like a gauge field with an index I, transverse, right? So, but in order for that to be the case, this thing needs to be massless. A photon is massless. So then if you impose this, it amounts to this quantity being 1, not just an integer, which implies that the dimension is fixed to being 26. And as written there, for the bosonic string, we have a similar formula. It's just that we have 2 types of A's and A daggers. We have A's and A tildes, right? But to conclude this, this idea, now we have a spectrum which is made of different kinds of fields, and actually an infinite number of different kinds of fields, because here we have well, I also goes from between 1 and 24, but also n goes from 0 to infinity. So all of these creation operators create different kind of fields. So string theory is like a field theory with an infinite number of fields, infinite number of types of creation operators. Yeah. So the question is why A is equal to 1, to say a little bit more. Well, this number operator, the lowest thing it can be is 1 if I have just an A dagger acting on the vacuum. So then I told you, then this index is transverse. So that looks like a transverse photon, right? But the transverse photon only the transverse directions and not also longitudinal is only in the case that the photon is massless. So that means that this thing has to be equal to 0. And so A must be equal to 1. Okay. Now for the so in this case we had a photon. In the case of open string, the massless object was a photon. In the case of closed strings, we said we have two kinds of objects. So we can have these kind of massless objects. So now we can see actually that we need two. So we need the same number of A's and A tildes. And that means that for the massless fields, I will not have something with only one index, but something with two indices. So let me call them phi ij. Massless fields are things that have two indices. And an arbitrary product of indices like this can be decomposed into a symmetric part, an antisymmetric part, and the trace. So this would be phi ii. Okay? So correspondingly, the massless fields are a symmetric object. That's a metric tensor. An antisymmetric object is something I will call B mu, and the trace is a scalar phi. So the massless fields, in this case, are a metric, antisymmetric tensor, and a scalar. And the logic of string theory tells us that we can have, so we can have lots of these particles creating, these are massless. So I can use Bose-Einstein condensation, or if you want, create a coherent state of these excitations. And these will create what? Will create a background of non-trivial G mu, B mu, and phi. So not just, a local excitation, but a whole background. So I have to consider then that the string actually moves in a background of these G mu, B mu, and phi. And the action is written there on page 34. I will not write it back. There's one problem with this construction. What I've told you until now is called the bosonic string. The problem is, like, you can look already at this open string mass squared. I said that for n equal 1, I need this to be massless. But then I get for the vacuum itself, so m squared for the vacuum is minus 1 over half prime. So that's negative, that's tachyonic, right? That's not nice. So one needs to get rid of this. And one gets rid of this by going to a supersymmetric theory. Just a moment, let me remember what I wrote here. All right. So we have superstrings. or supersymmetric strings. But what kind of supersymmetry? In principle, I can have space-time supersymmetry or world sheet supersymmetry. And that the one that we're more familiar with because, we can measure it is space-time. So this would be the Green-Schwarz formulation, in which one considers an object with space-time supersymmetry, but also a fermionic symmetry called kappa symmetry. And the point is then that one can fix a gauge for this. And the resulting theory has also space-time, also world sheet supersymmetry. All right, so how do I, so let me just quickly show you how we can have such a supersymmetry in space-time. Well, in the Nambu-Goto action, we had this object, the derivative of x mu. So now we write a generalization of this where I add an extra term that is quadratic in some fermions. So I introduce some theta A, which are space-time fermions. Okay? Spinors. Then in here I have to have by invariance, that's the only thing I can have, right? Well, with an I guess. So two fermions gives you a boson, then gamma A, well, yeah. Gamma A gives you the index A. Oh, sorry, no, what I'm saying here. No, this is dA, sorry, and gamma mu. So gamma mu gives you an index mu, and the covariant derivative, it's like this covariant derivative. It has to be acting on the field. And you can see that this is invariant under a supersymmetry that changes, that relates the bosons x mu with the fermions tau A through the formula written there on page 34. Yeah, this is annoying. Anyway, so the point is, now I can generalize the action. So before I had dA x mu, dB x nu, eta AB, g mu nu, right? And now I just change this to PA mu, PB nu. But moreover, now I can add also this extra term. So this is one term in the action, and I can also add this extra term, B mu nu, pi I nu pi b nu eta ab. Epsilon ab, excuse me. This is antisymmetric. Okay. Yeah, and in flat space, this b is the second term is the long expression there, page 35. There's also, as I said, this fermionic kappa symmetry, which, again, I'll not write it down. It's written over there. And is the gauge that is fixed amounts to this, gamma plus theta A equal to 0. And it's the fermionic equivalent of the light cone gauge that was considered before. And we said that when fixing this gauge, we get something with world sheet supersymmetry as well, because then this theta A alpha are regrouped into Majorana spinors. SM is world sheet Majorana spinors. So so when imposing the kappa symmetry, I can use the properties of spinors in 8 dimensions and make a regrouping of the components of the spinor into the components of this space-time spinor and world sheet scalar into an object that is a world sheet spinor, SM, and then the action becomes just 3 bosons plus 3 fermions. So dA xm, dA x, how I call it, xi, dA xi plus sm gamma dA sm. Yeah, I called it little gamma in this case. So we have an action with space-time supersymmetry, and after fixing a gauge for some extra symmetry, we get also an action with world sheet supersymmetry. And supersymmetry is good. Why? Because supersymmetry means for every boson, there's a fermion. And roughly speaking, you can see that the tachyon was by itself. So that cannot be. A tachyon is a scalar, and it should need to have a partner. So that, roughly speaking, means you get rid of unpaired states in the spectrum, including the tachyon. So now things are much better. And then, so this was Green-Schwarz, but there's also Neveu-Schwarz-Ramond string or spinning string. So this is sometimes called superstring. And this spinning string, the terminology just means when you think about super, you generally think of space-time. And so supersymmetry on the world sheet is called, because it has supersymmetry world sheet, you call it spinning instead of super. But you have to remember, both are supersymmetry, it's just different kinds of supersymmetry. And yeah, I'll not get Yeah, let me skip this part. I just wanted to say that the Navier-Schwarz superstring becomes, so it has two different kinds of states, the bosonic ones, or Navier-Schwarz, and the fermionic ones, or Raman. And so I wrote an action here for the Green-Schwarz in some gauge, and this becomes the same as the Navier-Schwarz action. So the two systems are equivalent in a gauge. So the two formulations are the same in a gauge. So yeah. Which term is not? So oh, sorry. Yes, yeah. I didn't put that. Yes, excuse me. Yeah, I should have considered it. I didn't even mention it here. So there's, I think, it talked about the coupling with the dilaton. The term, I avoided it simply because it's too much to say. But so I wrote for the action a coupling to the metric, the first term, in page 34, then a coupling to B mu, the second term, and a coupling to the dilaton, phi. And R2 is the two-dimensional Ricci scalar, so on the world sheet. And yeah, it should be there also in the supersymmetric case in principle, but yeah, I did not consider it. So, all right. So the only thing that is really important to say now, with respect to this NSR string, so the chirality of the two thetas. So I've noticed in here that I have two fermions on the world sheet. So in the Green-Schwarz there was thetas, and in this case there were psis, but in both cases we have two fermions on the world sheet. In principle, can be chosen to have either the same chirality, in which case we have the type 2b theory. So theta A, same chirality. That's 2b. And different chirality, it's 2a. So that will be important. That means that there are two different kind of string theories. Moreover, there's a third. We can, in principle, consider only one chirality, and then couple to some gauge fields. So plus SO32 Yang-Mills. So this is yet another type of string theory, type 1. And further, there are two more that I will not describe, SO32 and E8 cross E8 heterotic. So all in all, there are 5 different types of string theories. Okay. Conformal invariance. So yeah, so let me, I'm almost done, but I want to talk about conformal invariance. So do you have questions at this point? Yeah. choices, right? There are different, there are discrete choices. So I said theta A's. There are 2 theta A's. But I can choose them to have the same chirality or opposite chiralities. So if I choose them, so yeah. And then there are further choices. I can choose only one theta. I did not describe it, the action, but I can write a similar action where I couple to Yang-Mills theory. So that's type 1. And heterotic is even a little bit too complicated to describe quickly. So it means the left movers are bosonic, but the right movers are supersymmetric. And there is also discrete choice there. So all in all, there are discrete choices, meaning there are 5 independent string theories. Well, at this point, they seem independent. Later on, that was shown to be part of a bigger theory called M theory. But at this point, they seemed independent. Okay. All right, so let's see conformal invariance. What's conformal invariance? Well, so this is the second part of the name AdS-CFT. AdS stood for anti-de Sitter. CFT stands for conformal field theory. So what's conformal field theory? Well, there's conformal invariance that is actually a transformation of flat space. So the distinction is important because what we mean is we make a general coordinate transformation, but onto the flat space. And the conformal invariant theory, so when we do this, so the conformal transformation is such that I get here a factor, a conformal factor. And the conformal invariant theory means it's invariant under the appearance of this omega, right? So it's as if I don't have it, right? So it's important to realize this is then an invariance of flat space. The transformation I do is part of general coordinate transformations, but a specific one such that I get this factor. But the transformation is, the symmetry is a symmetry of flat space. Okay. So, in these transformations are different for dimensions greater than 2 and dimensions equal to 2. In dimensions greater than 2, they form a finite group. So it's just the transformation is SO d, 2. So if we're talking about our 4 dimensions, we have SO 4, 2. Okay. Remember, Lorentz is SO 3, 1. So this is bigger than Lorentz. It includes Lorentz. But in d equal to 2 is special because here is an infinite dimensional group of transformations. Namely, the transformations which are holomorphic. So z prime is f of z, where z is complex. So z prime is f of z, but not of z bar, right? Holomorphic. So that means that ds squared, which was dz, let's say dz prime, dz bar prime, is equal to dz bar f prime, f bar prime. And that's our omega squared. And And so it's an infinite dimensional group that forms an algebra called the Virasoro algebra. Whose form is written there, the commutator. And in 2 dimensions, we would have general relativity tensors, which would transform like there on page 38. We would have transformation of the tensor with dz prime over dz. But we define object called primary fields, which are a generalization of that. So so we would think of how would a tensor with some indices z and some z bar transform. And this would be by having dz prime over dz and dz bar prime over dz bar. Just that here and here we would have the number of indices. And the difference of the primary fields is that so-called number of indices is now an arbitrary number, real number. So, so these are not quite GR tensors, it's something else, but the analogy with GR is easy to understand what this means. Then in the case of conformal field theories, an important notion is the operator product expansion. Yep. It's only into the, no, sorry. The definition is in general. Yeah, I wanted, I used the 2-dimensional case just for, because it's easier to understand, is this relation to general relativity. The definition is the same, yeah. I mean, this is you can forget the thing I said about general relativity. This was just something to understand the transformation. So. All right. So the operator product expansion, in a quantum theory, when I have 2 operators at nearby points, x and y, well, sorry, xi, xj, let's say, better said, then in general, if these go close to each other, the idea is that one should be able to expand in operators at points well, you can choose either if they are nearby, it doesn't matter too much. So either at xj or xi or in the middle somewhere with some coefficients, ci, jk, that depend on this difference between the operators. And then the so if we are very close to each other, if the points are very close to one another, then all mass scales don't matter. So this is as if we are in a conformal field theory. And then, so mass scales shouldn't appear, so this coefficient can only depend on powers of this xi minus xj. It's just that now if you say that this has dimension delta I, this has dimension delta j, and this has dimension delta k, there's only one thing that can appear in here, delta I plus delta j minus delta k. And then you're left with simply coefficients, numbers, times OK xj. So in this case, yeah, and for energy momentum tensor is that formula on page 39. And for primary fields, another formula. But the important point is in this operator product expansion, you're reducing the relevant information to some numbers. Well, these dimensions, certainly, and these coefficients, Ci, J, K. And an example, our basic example and most relevant one of conformal invariant theory in 2 dimensions is just the string theory, which was dB x nu eta mu nu eta AB, right? So this was just an example of a theory that is conformally invariant. It can be written also, like I wrote there, in terms of complex variables. This would be 2dA, 2dx mu, d bar x nu, right? Yeah, and yeah, let me stop here. So the rest I will leave for tomorrow, because we don't have time, and it's a good moment to stop. So after that, the remaining points of lecture 2 are about T-duality and how that generates the idea of D-branes. All right, so please ask more questions. Well, in any case, I will come back at 3 for you to ask more questions, and I will give you some exercises to do, and you can ask me what you want about that as well. Yeah, okay. Yeah, okay. Yeah, go. Yeah. Yeah, so the question was, kappa symmetry is a symmetry of Green-Schwarz to put the theory in light cone gauge, and yes, that is true. So to put the theory in a fermionic light cone gauge, the equivalent of the light cone gauge for the fermions, yes. Okay. Yeah. So the question was, I said here that OPE is defined in a general theory asymptotically. So that is, so what I mean is it's valid in any theory, including QCD, any theory with a mass scale or anything, right? But the particular form I wrote over there with power laws, that's only valid in the conformal limit, that is to say in the limit where the points go close to each other and I can ignore all mass scales as being much smaller than. Yeah, because otherwise I could have put in exponentials, for instance, exponential of minus m xi minus xj, right? But so the operator product expansion is used a lot in conformal field theory, but let's not forget our phenomenologist friends, which use it for QCD all the time as well. Well, yes and no. My point here was that this was defined in a general quantum field theory, okay? So I said in a general quantum field theory, I can define, I don't need, in a general quantum field theory, I don't have conformal invariance, so I cannot talk about primary fields. Also, I don't need to, so this formula doesn't apply to only primary fields, right? It applies to any field. So, so then this relation I wrote over there is just, matching dimensions. So I say the field has some quantum dimension, and yeah. For the primary field in a conformal field theory, yes. Yeah. All right, let's take a break until 3, and then you can think about more questions, and I also give you these exercises. All right.